Good morning, girls. Welcome to our first day of online learning. I'm trying my very best to keep these videos under 15 minutes, really short and sweet, so that you'll be able to get some note-taking and then be able to work on some practice when we're all finished. I would strongly suggest that you print out these guided notes, so if you haven't done that, you can go ahead and hit pause now, go ahead and print them out, and then catch up with us. So we're going to begin kind of where we left off right before spring break in chapter 6. We were talking about radicals, and we're going to be transitioning a little bit into the real number system and then also looking at imaginary numbers. But for today, we're going to be looking at rational and irrational numbers, which is a little bit of a review. You may recall from the beginning of the year I had you all stand around the classroom with an index card of a number, and we categorized everybody into different categories like whole numbers and integers and natural counting numbers, and then we did talk a little bit about rational and irrational, and so we're going to touch upon that again today. Alright, so let's start off with a definition. Every real number has a decimal representation. So I'm going to get my pen started and write in here. So a decimal representation. So that just means that you can write a real number as a decimal, and every decimal represents a real number. So in example 1, we're asked to find a decimal representation for each rational number. So if I look at example A, this is 37/16. You may recall that the division symbol also looks like this. So even though this is 37/16, you can also say this is 37 divided by 16. And so you can just type that into your calculator, and you should get an answer of 2.3125. And we would call this a terminating decimal. Alright, so go ahead and pause the video, and then you can do B on your own and then check. Alright, so just like the other example, you can divide 19 divided by 22. And you should get an answer of 0.863, and then the 6-3 repeats across the screen. So we put a bar notation over just the 6 and the 3, and we would call this a repeating decimal. Okay, all right, let's scroll down. And look at this next example. All right, so now we're asked to write these terminating decimals as common fractions in lowest terms. So really, here's where we're going to be using our place value to help us out. So if I look at where this 1 is situated, and I recall my place value, so the 5 would be in the tenths, the 7 would be in the hundredths, so the 1 would be in the thousandths. So I could say this decimal, instead of saying 0.571, I could say 571 thousandths, which is the same thing as 571 over 1,000. And then I would look to see if I could simplify it, since it does ask me to find it in lowest terms. But this particular fraction does not simplify, so we're going to leave it as is. All right, let's take a look at part B together. So this is a mixed number because I have a whole number in the front. So I would read this using my place value. That 6 is in the hundredths place. So I could say 2 and 36 hundredths. And then I would look to see if I could simplify. And I could divide both my numerator and my denominator here by 4. So that would give me 2 and 9/25. And then because I'm asked to write it as a fraction, not as a mixed number, I'm going to want to put this as an improper fraction. So to do that, you're just going to simply multiply 2 times 25 and then add 9. So 2 times 25 is 50, plus 9 is 59, and that would be over 25. And that would be your final answer. All right, let's scroll down to our next example. So we are being asked to write these decimals that are repeating decimals as a common fraction in simplest terms. So this is a little trickier than the ones above because we're not going to be necessarily using place value. So I'm going to walk you through the steps for part A. So the first thing we're going to do is we're going to set our decimal equal to a variable. So I'm just going to use the letter n for example. So I'm going to say n is equal to 0.327 with the bar on top. And now I am going to manipulate this equation I just created by using the fact that there are 2 digits underneath this repeating bar. So I am going to multiply both sides of this equation by a power of 10 dependent on the number of digits under the repeating bar. So because there are 2 digits, I'm going to multiply by 10 to the power of 2, which is 100. So if I multiply both sides of this equation by 100, I would get 100n is equal to, and then when I multiply any decimal by 100, I just move my decimal point 2 places to the right. So this now becomes 32.727 repeating. Now you may be asking, why did I do this? Well, now here comes the magic part. So now what I'm going to do is I'm going to rewrite this original equation that I started with underneath, but making sure that I line up my decimal points. So n is going to stay here, and then I have 0.327 with the bar on top. And you may notice that my 27 and 27 with the bar on top are underneath of each other and aligned up. So now, if I were to, let's say, subtract these 2 equations from each other, I would get 100 minus n is 99n, and 32.727 with the bar over it minus 0.327 with the bar over it now becomes 32.4. So I've essentially eliminated those bars, and this is kind of where I want to get because I'm trying to write it as a fraction. All right, so let's solve for n. So I'm going to divide both sides by 99, and I get n is equal to 32.4 over 99. Now I can't have that decimal in my numerator, so I'm going to multiply both the numerator and denominator by 10 so that I get 324 over 990. And then now I need to simplify. So if I wanted to simplify this fraction, I could divide by 18. And that gives me an answer of 18 over 55. And now I can check my work. So if I want to take my calculator and divide 18 divided by 55, I should in fact get my original answer. So then I know that I did this correct and I can check. All right, let's go through part B together. So we're going to use our example from 3A, to help us. So in the first example, we set our original decimal equal to a variable. So again, let's just use the letter n for simplicity. So n equals 1.89189 with the bar over top. Now, just like in the last example, I'm looking at the number of digits that I have underneath of my bar notation, which is 3. So that means I'm going to multiply by 10 to the power of 3. So I'm going to multiply this side by 1,000. So it gives me 1000n. And then over here, I'm going to move my decimal point 3 places to the right. So I get 1891.89. And I still have my bar. Oop. Sorry. Made a little mistake here. Alright, so I'm going to erase that. Sorry, and I'm going to rewrite 189 outside here. Okay, so now let's take this and rewrite it underneath. So I have n equals, and again I'm going to line up my decimal points, 1.89189 with the bar over top. And again, just like in the last example, notice that this and this are lined up, and when I subtract, they will go away. So I'm left with 999n equals 1,890. So then I'm going to divide both sides by 99 or 999. And I'm left with n equals 1,890 over 999. And I need to simplify this, and this can be simplified by 27. And again, if you don't see the 27 right away, you could divide by 2 and then divide by 9. Or I'm sorry, divide by 3 and divide by 9. And then you could get an answer of 70 over 37. So we have our answer, and again, just check with your calculator. 70 divided by 37 does in fact give you the original decimal representation, so you can put a check next to it to know that you did it correctly. Okay, trying to keep true to the time, so let's scroll down to our final example. But before we do that, I do have a little definition for you to fill in. So the decimal representation of any irrational number is infinite and non-repeating. So if you think of the word irrational, usually when you think of someone who is like thinking irrationally, someone who doesn't make any sense. And maybe they go on and on forever. So this is kind of similar. So a decimal representation of an irrational is a number that continues on forever, but there's no pattern, there's no repeating happening. So if we take a look at the square root of 2, you can just type that into your calculator, and you should see that you get something like 1.41421 ... So you can see that it repeats, or I'm sorry, it does not repeat, it goes on forever. So it's infinite, but it does not repeat. So that is the very definition of irrational. So we would classify this as irrational. I'm just going to use IR to note that. All right, part B is one that we could simplify first. So we know that these are both perfect squares. So if I took the square root of 4 and the square root of 9, I would get 2/3. Now if I type 2/3 into my calculator, I should notice that it gives me an answer that looks like this, right? 6 repeats. So this is infinite, but it does repeat. So this is not irrational. We would call this rational. And I'm going to use an R just to say rational. All right, looking at this next one, letter C, I've got 2.03030303. So it looks like the 03 is what repeats. So again, this is infinite, but it does repeat, so therefore it is rational. And then our last example, I've got this 2.03005007, which kind of has a pattern to it, but it does not repeat, so therefore this would be considered irrational. All right, that about does it for us. Your homework is listed below, and you can go ahead and start completing that, and I will check in with you all through Google Meet very shortly. All right, thanks, and talk to you soon. Bye.